Okay, so today we are going to keep working through the relative efficiency part of lecture set number 4. In this unit of lecture set number 4, we are effectively just comparing the variances of different estimators for the population mean. So as a refresher, if we start on slide 55, which is the example we left off with last time. So in terms of sampling schemes, we have been working strictly with simple random sampling in this unit of the course, so in the lecture set 4. All right, so the parameter of interest could be one of 3 usual values, but actually we've now included the population ratio. But so for the purposes of relative efficiency though, and what we're really looking at here, suppose you have a parameter mu. Okay, we can have a statistic or an estimate. Let's call it an estimate. Which would be mu hat y. So this would be our SRS estimate. We could have mu hat ratio. This would be our ratio estimate. We can have mu hat regression. This is the regression estimate. And we could have mu hat diff, which is the difference estimate. Oh. Okay. So through lecture set number 3 and now lecture set number 2, through lecture set number 2 and now lecture set number 4, we have learned about 4 different ways of, say, estimating the population mean. Now we can do the same thing for the total or for the proportion. Well, we can do the same thing for the total for sure. For the proportion, it's a little trickier. So we'll focus on the mean and the total. And again, the idea is we have 4 different estimates for the same population quantity. And what we are asking here is which of these is the best. Okay, so the question is, which is best? Okay, if all of the estimators are unbiased, the best estimator would be defined as the one with the smallest variance. Okay, so the typical answer to this question would be the minimum variance unbiased estimator. So from an empirical or a practical point of view, what we are effectively asking is which of these estimators has the smallest variance. Now we could compare the variances directly. That would be a valid approach for the same sample size, to just calculate the variance of each of these estimates and then state which one is the smallest. The other approach that we can take is to use what is called the relative efficiency method, or the relative efficiency calculation. The relative efficiency is simply a ratio that compares the variance of one estimator to the variance of another. So for example, on slide 55, here we are comparing the ratio estimator to the simple random sample estimator. So we have the relative, in equation 7, we have the relative efficiency of mu tilde r over mu tilde y. So this is the ratio estimator over the simple random sample estimator. Now you can see that the relative efficiency of the ratio estimator to the SRS estimator is equivalent to the variance of the SRS estimator divided by the variance of the ratio estimator, which can be further simplified as shown in equation 7. Now, the way that we use the relative efficiency measure is fairly straightforward. Effectively, if this value is equal to 1, that means that the variances are equal, and that should be clear based off of the construction of the measure. If the value is greater than 1, that would indicate that the variance of the SRS estimator exceeds the variance of the ratio estimator. And if the value is less than 1 in this case, that would mean that the variance of the SRS estimator is less than the variance of the ratio estimator. So our interpretation of the relative efficiency measure is all about a value of 1. So 1 is equality, and then from there we can be larger or smaller. And then it simply just depends on which variance, which value is being placed in the numerator of the expression to determine which estimator has the larger variance. So to illustrate this approach, we looked at one example last class where we compared the ratio estimator to the SRS estimator for the data set given on slide 56, which is shown here. Okay, so we have the square foot basal area, which is our auxiliary variable in this case, and then we have volume, which we are considering to be the variable of interest. All right, so we want to compute the relative efficiency of ratio estimation to simple random sampling for mu y and for tau y. So for mu y, we can use the expression that was given on slide 55. So you can see here, I have exactly the formula given on the previous slide. I'm just subbing in for each of the different components in the expression, given the summary statistics that are shown on the slide. And that gives us a value of 15.3567, which is very large. So this is giving us overwhelming, well, this is implying that the ratio estimator is much more efficient or more precise than the SRS estimator, given the magnitude of this value. Now we can do the same thing for tau. And the interesting thing is that when you measure tau, you end up with the same relative efficiency. So for the same sample, the same set of information, and through the same comparison, the relative efficiency of the estimator for mu will be equivalent to the relative efficiency of the estimator for tau. Okay. Any questions? Okay, so in general, we expect the ratio estimator to be more efficient than the SRS estimator if the variation in the x values is small relative to the variation in the y values, and if there's a strong correlation between x and y. The second point is the point that we would expect to play a key role in reducing the variance of our estimator for the variable of interest. This is because, as we have previously established, the value of the ratio estimation approach is that it utilizes information from that auxiliary variable to improve our estimate of the parameter of interest. So we would expect that if we have information on this auxiliary variable and that auxiliary variable is strongly correlated with y, so it's actually contributing information, it's changing in the same way that the variable of interest is changing, that this would play an important role in our estimation procedure. Okay, we're going to look at a few more examples of relative efficiency here for some of the key estimates that we've talked about in the class. Then we're going to look at one overarching exercise, and then we're going to talk about ratio estimation within stratification fairly briefly, but this will be a pretty general extension of what we saw in this lecture set in the SRS case. All right, so the next estimate that we discussed in this lecture set was the regression estimator. So it would follow that we might be interested in comparing the efficiency of the regression estimator to the simple random sampling estimator. You can see here that we're really using the SRS approach as sort of the baseline approach for finding an estimate of that value of interest. Okay, so the setup for this is effectively the same as it was before. So when we compare the regression estimator to the simple random sample estimator for the population mean, we simply have a ratio of the variances. So again, here we have the variance of the SRS estimator of mu. And then here we have again, or we have, as you would expect, the variance of the regression estimator of mu. Right, so again, we have seen multiple ways of estimating the same parameter. So we have the simple random sampling approach. We have the direct estimate based off of a simple random sample, which would be the traditional estimate of the mean. And we also have the ratio approach, the regression approach, and the difference estimation approach. And we're developing a way to compare them, given that we know the smallest variance would mean the best estimate. All right, so we can show that this particular relative efficiency measure can reduce to a very convenient form, which is shown in number 9 here. So this is saying that the relative efficiency of the regression estimator to the SRS estimator is simply equal to 1 over 1 minus rho squared. And that would mean that this is an approximation of the variance of mu tilde y divided by the variance of mu tilde reg. And it's helpful to remember the structure of the variance expression or the variance fraction when working with the relative efficiencies, because this can help us to correctly interpret the result that we get from this particular set of work. All right, so quick illustration of this idea here. So we want to compute the relative efficiency of the regression estimator to the simple random sampling. To simple random sampling when estimating mu. This should just be mu. Well, we'll call it mu. All right, so we have here the relative efficiency of mu tilde reg over mu tilde y is equal to the variance of mu tilde y over the variance of mu tilde reg. So this from the previous slide is going to be 1 over 1 minus rho squared, which is equal to 1 over 1 minus 0.9712, which is equal to 16 points. So we can see here again, so this shows that the regression estimator is more efficient than the SRS estimator. Now we'll also notice here we have a value of 16.03176. When we compared ratio estimation to the simple random sample estimate, we had a relative efficiency of 15.3567. So what this is showing us is that for this particular example, we have evidence that including this auxiliary variable is very beneficial to the estimation process. And what we can also see is this value of rho here, this is very high. So that implies that there is a strong correlation between, in this case, the square foot basal area and the volume of the trees that we are measuring. So it's not surprising to see that ratio estimation and regression estimation are providing estimates that have a smaller variance than the traditional simple random sample estimator. Further, seeing that the value here, oh yeah, thanks. Further, seeing that the value here, 16.0317, compared to the value that we found in the previous illustration of 15.3567 are quite close together, also provides us with some verification that the values that we are returning are most likely the correct values. I also wanted to point out here that the comparison for the regression estimator to the SRS estimator can further be simplified in a different way. So we have this simplification shown here. And we noted on the previous slide, so technically, for large n. Now, if we wanted to compare the variances directly, so if we wanted to make a direct comparison, we can show that the relative efficiency of mu reg to mu tilde y, which we know is equal to the variance of mu y over mu reg. So this becomes 1 minus little n over capital N times sigma tilde squared over n divided by 1 minus little n over capital N multiplied by the MSE over n. Okay. So this actually reduces in a very nice way to sigma tilde squared divided by the MSE. Okay, so we can see here that these variance approximations really just boil down to a direct comparison of the variance term that's being utilized within our expression for the variance of the estimator. Okay, well, there's probably just a mistake then. I'll check it. Any other questions? All right. So we just mentioned the first point on the summarizing slide here. So that expression we use that involves rho is typically only valued when capital N is sufficiently large. However, we can show that the comparison reduces strictly to the ratio of sigma hat squared divided by the mean squared error for the problem at hand. Right? Okay. So we can compare our regression and ratio estimation variances to each other directly, as you can imagine. We can also compare the regression and the ratio estimators to the difference estimator as well, if we're interested in making those types of comparisons. Again, all of these comparisons boil down to the same idea of just taking a ratio of the variances of the estimators that we are using for the same sample size and ideally for the same sample. So we're getting an idea of which measurement would be the best for the problem at hand. If we compare the regression estimator to the ratio estimator, you can see again, we start with the same ratio of the variances, and then we have a simplification shown below that involves the variance of each of the individual variables and the ratio estimate itself directly. And then at the end of slide 62, we can see some different cases that would indicate when the regression estimator is going to be more efficient than the ratio estimator. So for example, when the correlation multiplied by the standard deviation of y minus the ratio estimate multiplied by the standard deviation of x squared is greater than 0. So this would be one situation where the regression estimator would be more efficient than the ratio estimator. All right, so as an example here, we should be able to show that the relative efficiency of mu tilde regression to mu tilde ratio, which is equal to the variance of mu tilde ratio. I think I need to have this here, divided by the variance of mu tilde regression. I guess we could try and do it this way. We'll have to get an estimate of theta. Let's do it the other way. So following from what we did on the previous slide, we can always get a direct estimate of the relative efficiency simply by simplifying the variance expressions. So here we're going to have 1 minus little n over capital N multiplied by, no, I should probably do it the traditional way. Okay, so we're going to have here, so this comparison is equal to sigma squared y plus theta hat squared multiplied by sigma hat squared x minus 2 times theta hat times rho sigma squared x sigma squared y divided by sigma squared y 1 minus rho hat squared. Okay, now we will need a few other things from the previous illustrations. All right, so from, actually, I'll write this down here. Okay, so from slide 55, I think it's going to be. Sorry, one sec. Just going to make sure I get the numbers right. 56. Okay. So from slide 56, we have that theta hat is equal to mu hat y divided by mu hat x, which is equal to 21.194. Okay, and then we have everything else that we need for this calculation. All right, so let's see what we get here when we work this thing out. Okay, so all right, 195, pretty close. Okay, so sigma xy is 1.0833. Sigma 2 dot x is 0.04629. Sig 2 dot y is 26.78. Rho is 0.9712. Okay, so we have sig 2 dot y. Should expect these to be pretty close together. Let's see if this works out. plus theta dot hat squared times sig2 dot x minus 2 times theta dot hat times p times square root sig2 dot x times square root sig2 dot y divided by definitely something wrong there. All right. Well, that didn't quite work out the way I thought it would, but we should be able to, well, all right. So we should be able to show that this is going to be in the area of approximately 1.04396. However, there's definitely something that's a bit off here. So I'll need to go back and correct this. Correction needed to values. That word is correction to values. So this part here, the in red, I'll take care of this and I'll just make a little note on the slide once I go to post it afterwards. But there's I either made a mistake when I tried to calculate this directly or one of the values on the slide is off. So I'll just need to check those values afterwards. But given that the relative efficiencies for the regression estimator and the ratio estimator to the SRS estimator were pretty similar to each other. So we had one that was around a value of 17 and one that was around a value of 15. The relative efficiency of the regression to the ratio estimator should also be very similar. So they should be in the area of 1.04396, but I have something that's off here. So I'll just need to check it so that I can give the right value when I go to use this formula. But I'll post that correction afterwards. Finally, we can also compare the difference estimator to the SRS estimator. Same idea again. So we can use the expression given in number 10. The goal here is exactly the same. And then if we wanted to, we can compare the difference estimator to the regression estimator or compare the difference estimator to the ratio estimator. Here, right? And again, the goal of all of these is effectively the same. Okay, so in the last illustration of the relative efficiency approach, we have a different data set where we're measuring the impact of the new drug and the standard drug on each of these different rats. I'm not exactly sure what it is that we're measuring here. My guess might be like body weight or something like this. So we want to compare the regression estimator to the difference estimator when estimating mu y, and we want to compare the relative efficiency of the difference estimator to the ratio estimator when estimating the mean. All right, so I was working on this one just before to touch some things up, and I noticed that I actually have quite a few things backwards here. So I need to point out a few corrections for this particular slide, and then we can show that all these values actually work out pretty nicely. So here we have the following. So mu x. So basically the I have the symbols backwards. So this is y and this is x. This term is fine. This term would also be y. This term would be x. This row is fine. Yeah. The MSE, so this value here should be 0.197. And then the diff is good. Right, so I just had the symbols flipped and then my MSE was a bit off. All right, so to work through these approaches, I prefer to take the direct approach. So in part A, we want to do regression to difference estimation. Okay, so in part A, we have the relative efficiency of the variance of mu hat reg divided by the variance of mu tilde diff. Okay, so this is going to be the variance of mu tilde diff divided by the variance of mu tilde reg. Oh, sorry, and I don't need the variances in here. I just need the estimators. Okay, so we're going to have here 1 minus little n over capital N times what we called sigma hat d squared over little n divided by 1 minus little n over capital N multiplied by the MSE over little n. So you can see what happens here, again, is that we get a really nice simplification, even nicer than the one shown on the previous slide, where we have sigma d over the MSE, right? And then as a reminder here, so sigma hat d, this is going to be the sum of I and S of each di minus d bar squared over n minus 1 divided by the MSE. So using what's given on the previous slide, we should be able to show easily that this value is equal to var diff over var reg 0.945. All right, and then in the second illustration, we want to do the ratio efficiency difference to ratio when estimating the mean. All right, so let's do this in the same way we did it above. So we're going to have mu tilde ratio divided by mu tilde diff. So this will be the variance of mu tilde diff divided by the variance of mu tilde ratio. Okay, so this is going to be 1 minus little n over capital N, and then we're going to have the sigma hat d again over little n divided by 1 minus little n over capital N, and now we will have sigma hat ratio, these are all squared, divided by little n. So this is going to give us sigma hat d squared over sigma hat ratio. And now the only thing that's kind of a pain that we don't directly have on the slide is the value of sigma squared ratio. So we need to work this term out. All right. So this term here, which is sigma squared hat ratio, This is going to be the sum from I, or the sum across I and S of the yi minus theta hat xi squared divided by n minus 1. So you can use this as practice for the assignment if you want, actually, because we have to compute this value in question number 4. But we can show that this value, so theta hat here, is equal to 0.97787. So this is going to be the sum I and S of yi minus 0.97787 multiplied by xi all squared divided by n minus 1. And if we work that summation out, we should end up with something in the area of 0.19597. Okay, and then if we compare that to the variance of the difference, we get 0.9500. And that feels like a very reasonable result because you can see that the ratio and the regression estimates are actually very close to each other when compared to the difference estimation, which I always find to be kind of a validation of what's actually happening. Okay, so that is probably way more than we needed to see on relative efficiency. In hindsight, it probably would have been fine just to say that it's a comparison of the variance and then show a few different examples of that. But live and you learn a bit, I think, in this situation. So I'm going to check this stuff on that one slide. Again, relative efficiency is basically just a comparison of the variances that we can use across the same sampling schemes for the same sample sizes. We know that sample size is going to change the variance of the estimate. So the larger the sample size, the smaller the variance of the estimate is going to be. So it wouldn't be fair to compare the variance of, say, the regression estimator using a sample size of 100 to the ratio estimator using a sample size of 20, just for example. So we typically would use these for the same sample so that we can get a sense of which estimator is working the best in that particular problem. And that's really the point of exercise 4 on the assignment. Okay, there's one other topic that I wanted to talk about in this lecture set, which is ratio estimation in the context of stratified sampling. So we have seen ratio estimation in the context of simple random sampling. We can extend this idea to stratification in a fairly natural way. So as you will recall, what stratification is essentially just a division of the population of interest into different sectors. So within each sector, once we stratify, we're actually just performing simple random sampling to get our estimates for the variance of each strata and our estimate for the mean of each strata. And then all we do is we weight those estimates using the strata proportions. So for example, the mean across 3 strata is going to be the strata weight multiplied by the SRS estimate from that strata summed together. And then the variance is the same idea, except that we square the strata proportion because of how the variance operator works. So it follows pretty naturally that one approach to applying ratio estimation within the context of stratification is to separate into your strata. And then once you're within the strata, you can use a direct ratio estimation approach to find an estimate for the mean. Okay, so you have stratification, you split the population into different sectors. Now that you're into different strata. And now that you're within that strata, you're really just conducting a simple random sample within the strata. So you can do all of the things that we just talked about, direct estimation, ratio estimation, regression estimation, and difference estimation, and form a strata-based estimate of that value and then weight it afterwards. Now, it also follows that you could also do what is called like a combined ratio estimation approach, where you um, build your estimator while taking into account all three strata at the same time. But yeah, so that's going to come up a little bit later. Okay, so I'll show you an example of how that will work from a mathematical standpoint momentarily. But following up on what we were saying about the separate ratio estimator approach, which would be the more natural approach to using ratio estimation within the context of stratification. So here on slide 70, we have theta hat SR. So this is the estimate of the population ratio based off of separate ratio estimation. Okay, so you can see here that this is just simply a ratio estimate for each strata, right? And then we're just weighting that estimate based off the strata weight. So that's exactly the same idea that we saw before when we first introduced stratification. So we break into different sectors and then we perform ratio estimation within each of the sectors or strata. I don't know why I keep using sector to describe strata today. And then the variance term is the same idea. So here you can see that we have the finite population correction for each strata. So this is the variance of each strata. Right, so this is the variance for each strata directly. And you can see that this has the exact same form as the population ratio estimate that we utilized in this lecture set when we first introduced simple random sampling. So this is not the combined variance across all strata. This is the individual variance for each strata. So the unweighted variance. And then this term here, the sigma hat squared theta h, that's the same definition of sigma hat squared r that we actually just looked at in the previous illustration. It's just within each of the strata. Right. Okay, so we can then show that the ratio estimator for mu y is going to be basically just the weighted the weighted ratio estimator within each of the strata. So mu hat y SR, this is a direct extension of mu hat y r, or mu of mu hat ratio or mu tilde ratio that we studied earlier in this lecture set. It's just weighted across the strata. And then now we can see an equation that represents the combined variance across all of the strata for the population mean estimator. So you can see the only difference here is that we basically have our SRS style form in this variance expression, but we're summing across the squared weights for each of the strata. Okay, so I'll stop there today, and then on Monday we'll see some examples of this and we'll just go over the ideas again. And then we'll probably start cluster sampling, which is the next unit in the class. So for assignment number 3, if you need till Monday, that's fine. I'll post an update on the website. And otherwise, if you guys have any questions, please let me know. I have office hours after this. And if not, have a good weekend. And I'll talk to you on Monday where we'll pick up with the ratio estimation within stratification stuff.